let's go and get started. Let me get the lights and whatnot adjusted. Okay, so let's sort of take today step by step so we get through everything we need to get through. Today might be somewhat short because after my last example, it's just that, it's my last example. So we have done pretty well this semester, and buckling is our last real topic. So yeah. And on top of that, just because I'm such a nice guy, we'll say, what the heck, no class on Tuesday. No, Thursday is going to be our review day. Yeah, we'll turn your last homework will be due on Thursday. I'll give you the solution. We'll have our exam review on Thursday. Does that sound fair? Okay, all right. I'll send an email out to the class confirming all that and everybody so that everybody knows what's going on, but yeah. Okay, so let's get a couple things out of the way. First off, sign-in sheet. Let's get that passed around and get that started. Okay. Excuse me. Today is December 1st. That is correct. Yes, it does. Okay. Next, I uploaded homework 8, the buckling homework, on Blackboard, but I forgot to print off hard copies. Sorry about that. Last time, so I've got hard copies for you today. It's 3 problems. 3. There's 2. 2, and then 3. Okay. So does everybody have a copy of homework 8? Everybody has a copy of homework 8? Okay, all right. So there's that. Actually, the sign-in sheet, can I see it real quick? Now I'm going to make things complicated. All right. I'm going to pass this around again because I want to pass around the notebook, okay? Now, I did take out the solution to homework 8, so you all don't have that yet because I just assigned the homework, so you don't have the solution. No jokes or anything. Okay, this is everything, though. Every homework assignment, every solution other than the solution to homework 8, every lecture note, every supplement. Give it the once over. Make sure you've got everything, okay? Sound good? So sorry about that. So if you're missing anything, go ahead and just mark it down and then go through that. Yes? No, I got you. Because there was only, I think, 2 people that were absent because I had them down, so you're good. Okay, last thing. So if you recall, I'm giving everybody 10 bonus points for completing their course eval. There's 20 people in the class, and I've only got, here's the thing. So I checked this a little bit ago. Keep in mind, I don't know who's done them. I can only determine how many are completed. Now, I've heard from 5 of you specifically that have told me that you've done it, but I know 6 people have done it. So somebody didn't tell me, and that's okay, that's you. All right. All right. Okay. I send a confirmation email to everybody letting them know that I got it. So let me mark you down. And then right here.
What's the deadline for that?
The deadline is December 9th. I think it is. And I know everybody's like, oh, well, December 9th. All right, I'll put that off to the last minute. And then what happens is you put that off to the last minute, and then you kind of just don't do it, I know in structural analysis, like the majority of the class has already done it. So, I mean, I would just, if it was me, I would go ahead and just knock it out. If you send me a screen capture that just, I don't want to see what you wrote. I just want to see that you've done it. I mean, some people have sent me their completed survey list. Some people have sent me a little screen capture that says they have no more surveys left that they can do or anything like that. As long as I see that you've done it, 10 points. And if you look on Blackboard, there should be a column that says course eval. And if you've done it, and I heard about it before class started, you should have 10 points. Remember, that tacks on to your accrued points on your homeworks this semester. So if there were a total of, I don't know, 250 homework points throughout the entire semester, then you could earn 260 points. You could earn 10 more. So you can get a homework average above 100%. Does that make sense? So, so don't forget to do that. I will probably, depending on how things go, I will send a reminder email maybe Wednesday, something like that, just to make sure everybody doesn't forget. Again, it's free homework points. Okay, who did not get homework 8? Did you? I think you walked in late, so. No, I didn't have it last class. I handed that out a couple minutes ago. Okay. I'm trying to think if there's anything left that I need to discuss before we get back into buckling, and running a blank. I don't think we have anything left. So with that, let me sort of get situated, and we'll get back into columns. Okay. We'll go right here. Okay. So let's go ahead and get back into columns. Now, last time we did our mathematical derivation for the buckling load and the buckling stress of a given a compression element. In other words, you've got some element that has some length L, some modulus of elasticity E, and then we also introduced not only moments of inertia and area, which we had heard before, but we introduced a new term R, the radius of gyration. Okay? Based on those properties, we can determine the buckling load as pi squared EI over L squared, or the buckling stress as pi squared E over the slenderness squared. Now, when we did our derivation, we did that for a simply supported column, and we said, well, what if you've got a column that's fixed on both ends, or fixed on one end and free on the other, or what have you. So to handle that, we introduced the effective length factor K. So for a pen-pen column, K is 1, and that's just the same thing that we originally derived. But if your boundary conditions change, for instance, if you've got a fixed column, your K value goes down. If you've got a fixed free column, your K value goes up, and what have you. These are exact values that you can derive. I mean, we can go through it if you would like, but it's really just applying different boundary conditions to your DiffyQ and solving it. It's not that difficult. Well, the math is a little different, but it's not too bad. In design mode, sometimes design codes specify that you should use values that are a little bit different. For instance, in steel design, the theoretical fixed K value is 0.5, but when you're designing a steel column, the spec usually says, well, or the way the spec treats it says, well, there's nothing that's purely fixed. You know, nothing has infinite fixity. Usually, I mean, you can have a really stiff connection, but it's going to rotate a little bit. So theoretical values would be 0.5, but for design purposes, they say, let's bump that up a little bit, and you would use 0.65. That's what the steel spec delineates. And there's a table in the back of the steel manual. If you take steel design, you'll see, okay, here's the theoretical value, here's the recommended value for design, and things like that. Okay, but since this is really kind of a theoretical class, I mean, that's really what this whole class is about, is learning the theory. I mean, what you will do, whether you're a civil engineer or a mechanical engineer, what have you, you're going to take this theory and apply it to different situations. Reinforced concrete beams, or steel columns, or what have you, or gears, or bearings, or stuff like that. I mean, whatever you mechanical engineers do, right? No, but in all seriousness, you're going to take these ideas and apply them to your own respective settings, and the theory is going to be the same, but the applications are going to be a tad different. So we're going to stick to the theory in this class, and then later applications will be left for future courses. Now, our last column problem is a design problem. So the question is, we have a square steel bar that supports a load of 20,000 pounds and on a length of 10 feet. We're given the value for E, and if the ends of the column are pinned, so what does that tell us? If the ends of the column are pinned, K is 1. If the ends of the column are pinned, determine the required dimensions of the cross-section, assuming that the allowable stress is 10 KSI, and assuming the allowable stress is 4 KSI. Now, we'll be able to use these these relationships to size the column, but I want to go back to what we talked about last time before we really start to explore this this particular example. Do you remember last time when we talked about the difference between how a yardstick fails and how a log fails? Remember that? So what that means is, for one of these situations, we may be designing a yardstick and it might be controlled by buckling. And another situation, we might be designing a log and it may be controlled by just F or sigma equals P over A. We don't know until we start exploring the math. So we'll start digging into it, and I think you'll see how things go, and it's going to be pretty straightforward. All right. Sound good? All right. Let's see. It's our last example. It's kind of sad, isn't it? You're like, yeah, sure. If by sad you mean jubilation. It's still too early, right? Is that what it is? Here, you can have a Canadian nickel if you want. There we go. Go buy a soda in Winnipeg or something. Okay, let's start off with section properties. Now, what I'm doing right here is I'm saying, all right, keep in mind we are designing the column, but we know for a fact that this column has what cross-section? What's it look like? Say it again? It's a square column. Okay, so I'm going to use that to help derive some parameters and whatnot that we can solve for. Okay, so in other words, if it's a square column, if it looks something like this, oh, that's horrible, right? And this is B, and this is B. What's the area of that column going to be? B times B or B squared? Now, what's the moment of inertia of that column going to be? First off, the nice thing about this is it doesn't matter whether we're talking about Ix or Iy since the dimensions are the same. So what is the moment of inertia? I mean, what's the moment of inertia of a rectangle? BH cubed over 12, so since h and b are the same, it's b to the 4th over 12, right? Right? Make sense? Now, reason why that's important is because I want to look at r squared, which is I divided by A. So that's going to be b to the 4th over 12 divided by b squared, or b to the 4th over 12 times 1 over b squared, which is b squared over 12. Therefore, r is b over that. What do we think? Does that sound good? Okay. Everybody good? All right. Now, let's now look at the column properties. Okay, column properties. Now, remind me, what did you say about K? What was K? 1. And we're saying that because we've got a column that's pinned. Right? All right. So that's K. So what's KL? Say it again. 120 inches. So it's going to be 1 times 10 feet, which is 10 feet, but we ought to go ahead and right now say 120 inches. because we're going to need inches because of our E, it's in KSI, and our moment of inertia is going to be inches to the fourth. Might as well use consistent units across the board. So that's KL. I'm going to compute a couple other things just to make my life a little easier. What is KL squared going to be? You say 14, what, 400? Is that what you said? Yeah. 14,400 square feet. Or square inches, sorry, square inches. All right, sound good? Okay. Next, I'm going to do a couple other things. I'm going to try and come up with an expression for slenderness, okay? So let's look at KL over R. We'll put that over here, KL over R. So KL over R is going to be 120 inches divided by B over the square root of 12. So could I say 120 inches times the square root of 12 divided by B? Is that a fair way of putting that? Everybody okay with that? Okay. Now, reason why that's important is because I want to look at, getting ahead of myself. I want to look at KL over R squared. So KL over R squared is going to be 120 inches times the square root of 12 over B, better than that, B squared. So all we got to do is square each term. So, bless you. So that's going to come out to be 14,400 square inches times 12 over B squared. Everybody see how I did that? And the square root of 12 squared is just 12 because terms cancel. Okay. So what is 14,400 times 12? There you go. Exactly right. Sound good? All right. Any questions? All right, do you mind if I go ahead and go on to the next panel, or do y'all need some time to write this down? Okay. All right. So part A, what do we know about part A? We know that, what were we given? We know that P is what? What load are we putting on the column? 20 kips, I think it was like 20, it was listed as 20,000 pounds or 20 kips. And we know that sigma allowable is what? 10 KSI. All right. Excuse me. So what we need to do is we need to solve for B, okay? Now, what I'm going to do for part A is this, is I'm going to assume buckling governs. Now, if buckling governs, let me ask you this. How do I compute the critical buckling load of a column? And how do I do that? Sounds good, right? Now, let's start plugging and chugging, okay? What is I? B to the fourth over 12, okay? So let's do this. Let's do b to the fourth over 12. Let's do it like that. And what is KL squared? All right, sound good? All right. So this is pi squared e b to the fourth over, what, 17 800 inches squared. Does that sound reasonable? So what I propose is we plug in our P of 20 kips and we ask ourselves what dimension of the column is required to resist that buckling load of 20 kips. Make sense? Sound good? In other words, we can say P is pi squared E b to the fourth over 17 800 inches squared and solve for b. So how about we do this? Would you agree that b to the fourth is going to equal p times 17, whoop, getting ahead of myself, 172 800 inches squared over pi squared e? Do you agree with that? Not too bad, right? So let's solve for b to the fourth. Now P is 20 kips. Pi squared, and what was E for this? I can't remember. 30,000. So what does that come out to be? Oh, he's making us do math again? I'm getting tired of this. It's too early for all this math. Yeah, that calculation with the pi gets a little, that gets irrational. Well, pi's are a rational number. What's that? Oh, come on. 0.67. Now, what are the units? What are we solving for? We're solving for b to the fourth, so inches to the fourth. So how do I solve for b? And what is the fourth root of 11.67, what have you? Say it again. 1.85. I'm going to drag it out one more place. 1.848. Is that good? Okay. Now, I'm going to say that that's the answer, but I'm going to check that answer. All right. Sound good? Now, let's just keep this basic. All right? If I have a column that has 20 kips on it, and it has dimensions of 1.85 by 1.85, how do I determine the stress on that column? Ignore all this buckling stuff. P over A, right? Let's see what the stress on this column is. Now, what's the area? What's the formula for the area? B squared. What does that come out to be? Say it again. 5.856. We'll just say 5.85. It's 5.86. Is that acceptable? Why is it acceptable? Well, yeah.
Allowable is 10
Exactly. The allowable stress for part A is 10 KSI. We're good, right? Now, that makes sense? Okay. I propose that with part A, we're designing a yardstick. In other words, it's going to buckle before it yields. Make sense? Now I want to look at part B. What's the difference between part A and part B? The allowable is 4 KSI. So let's use our noggins. Let's say that with part A we had an allowable stress of 4 KSI. Let's work through the math. So we would have done all of this, and we would have gotten a B of 1.85 inches, right? And then we would have checked, and we would have found that, yeah, this is the load required to, or this is the dimensions required to prevent buckling, but we would have violated the allowable stress before buckling occurs, right? Make sense? So would you agree that part B is more like the log? It's going to crush before it buckles. Make sense? So in that case, here's how you do part B. So part B. I'll say from part A, yielding governs. So here's how this works. Sigma allowable is 4 KSI, right? P is 20 kips. How do we solve for the required dimensions? Because we're looking at yielding and we're just looking at the log crushing, we just say sigma equals P over A. So A is P over sigma, right? See how I'm doing that? What is the area of a square column? B squared. So B squared is P over sigma. Therefore, B is the square root of P over sigma allowable, which is 20 kips over 4 KSI. And what is the square root of 5? Does that make sense? I really want that to make sense. That's an important concept to master. The idea that, yeah, we can solve for the dimensions required for buckling, but it doesn't matter because for part B, it's going to crush or it's going to yield before it buckles. It's like the log. I can solve for the required buckling load of a log, but if I put that under a press, the log's going to crush or splinter before it buckles. Does that make sense? Pretty straightforward, right? Not too bad. All right. Everybody good? Okay. So a little bit of housekeeping. Where's the notebook? All right. Have y'all had a chance to look through it? Okay. Has everybody had the chance to look through it? Who hasn't? What's that? Okay. All right. Well, the solutions, the homework solutions. I don't know if you have all those. I don't post those. All right. I'm going to leave that in here. If you haven't signed the roster, it's in the notebook. Okay. So make sure that you sign the roster. Let's see, a couple last points. If you haven't done your course evals, do it. If you send me confirmation that you have completed it, 10 bonus points on your homework balance. I have no more topics to cover because that's it. That is mechanics of deformable bodies. So here's how this is going to work. I'm going to hang out here for a little bit, make sure everybody's had a chance to look through the notebook and determine, that they have everything. You all have homework 8. Homework 8 is due next Thursday. You all have turned in homework 7, okay? What I might do is sometime next week, I might put homework 7 solutions in the box outside my door. Then you all can just come and grab them, at your convenience. We'll talk about homework 7 and homework 8 solutions on Thursday. I will prepare an exam 3 review PowerPoint. I'll let you all ask exam review questions just like previous times. Probably for the final exam, the way it will work is instead of having 3 questions and some conceptuals, we'll have 4. I mean, we got 2 hours, and there are a couple more topics, so we'll probably have 4 questions and conceptual. But you know how it is. Let's say they're not long questions, but each one's going to be on a particular topic, and they're going to cover the appropriate areas. Any other questions? Does anybody have any other life, anything, I'm not the person to ask. All right. So we will get back together next Thursday. Since this is the end of the teaching, I have to say this is one of the more fun classes that I get to teach. I have a blast doing this class, even though it's 8 o'clock in the morning. I can tell you all are having a hard time containing your excitement being up this early every day, semester, on gray December mornings, right?
So do we meet Tuesday?
We're not going to meet Tuesday. No meeting on Tuesday. I will send an email to the class, do the whole official, do my diligence and say, all right, everybody's done it. If you've got your course eval done now and you have it on, like you pull it up on your phone, I've had people just walk up to me and say, I've done it, and then I just mark them down, so that's fine too. That's it. That's all I got. I apologize for delaying or maybe increasing the stressful period between now and dynamics. Right? Because now you just get to sit in the lobby for the next hour, right? I apologize for that. But hey, we're not having class on Tuesday, so that's not so bad, right? All right. That's all I got, guys. You have a question?
I have a question on homework.
Okay. All right. Everybody's like, you kidding me? All right.